But now, for purpose of actually evaluating this integral, we'll do what we did before and fill in the parameterization. So z of t, that would be t squared. And dx is now going to be x prime of t dt. So that's going to be 2t dt. And then we'll fill in x, that's t squared again, times dy. Well, y is t cubed, so we're going to have 3t squared dt. Plus y, which is t cubed, dz, so that's going to be 2t dt. Okay. And so this will be the integral from 0 to 1, since that's a range of our parameter values. So then you can just multiply all this out and you get a single integral with respect to t. Right. So, so in effect what's happening is, suppose you have a closed curve. You have a curve C that goes from this point to this point. We'll call it C1. Then we have another curve, C2, that runs from the same at any point back to the starting point. So this would be an example of a closed curve. So an important question would be, is the integral over the curve, let C be equal to C1 plus C2, so C is the entire closed curve. If you're given a vector field, is the integral of a vector field over that closed curve equal to 0 or not?
Yes.
Well,
What? I'm gonna find Dr. Mead. He told us this.
if it is 0, then what you have a situation where you have an integral that's path independent. So the amount of work it takes to move an object from this point to this point is independent of a path taken to get there. Now, I'm going to describe a circumstance under which this integral is 0. Okay, and think of this as a preview for what we'll talk about on Tuesday. Suppose that f is the gradient of some function little f. So in other words, big F is a conservative vector field. And we're dealing with dealing with any curve C right now. It's not necessarily closed. And so we have a parameterization, R of t, where t runs between a and b. Then the line integral of a vector field over a curve. I'll just fill in the parameterization right now. So this is what you'd actually be evaluating. There's a dot product in here. But now I'm going to fill in the fact that big F is a gradient of little f. So we have gradient of little f evaluated at R of t, dot product with R prime of t, dt, but this whole expression here, what exactly is that? Or what does it remind you of? Think this case where if f is just a single function rather than if we're just dealing with a derivative with respect to x.
It's like a composite.
Yeah, it is a composite.
Okay.
So this whole thing is the derivative with respect to t of f composed with r. T. So what that means is we can just anti-differentiate this and get little f of r of b minus little f of r of a. So when we know that our vector field comes from this, if we can identify what this little f is, then this line integral of this vector field is very easy to evaluate. So this is what's called the fundamental theorem of line integrals. And you can see how it closely relates to the fundamental theorem of calculus. If you bring this down to just one dimension, kind of is a fundamental theorem of calculus, combined with the chain rule though. All right, so now this is what we have. So what if the curve C is closed? What's going on in that case? What can we say about this? So the starting point at t equals a is the same as the ending point at t equals b.
It's an integral over nothing.
Well, you're still integrating over a curve. A curve itself is not nothing.
Okay.
But if we look at the value of the integral, because yeah, so a and b are still different. But now we plug a and b into a parameterization, and we get the same point. So what does it say that about this value here?
They have to be equal to one another.
What?
The FRB and FRA have to be equal.
Yes. Because you're plugging the same point into f. So the value has to be 0. So if you have the line integral of a conservative vector field over a closed curve is always going to be 0. Okay. So, all right, I'm just about out of time. So, but we will continue talking about line integrals on Tuesday. More about this. So hopefully the rest of you can make it to the review session.
See you next time.
Yep.